So the second translation properties that we had, not that f of s minus a stuff, used what's called the unit step function, not unit step function. Or it's also called the Heaviside function. And it's that u of t minus a, which is given by 0 and 1, for 0 less than or equal to t less than a, and a less than or equal to t. I'm going to sketch it out for you so you see what it's doing. It's a function in time. And all that's going to happen is it's 0 for a really long time until we reach t equal a. Then it hops up to 1, and then it's just 1 all the time. That's all the function does. It can be helpful to think about it like an on-off switch. So u says off for 0 to a, and then when you hit a, it says on. And the way we're going to use it is it's a way to represent in a single line piecewise functions. That shift their definition at t equals a. So we have solved differential equations that have piecewise parts. If we wanted to do that with Laplace transforms, we would have to be able to write L of that function. And we don't know L of curly bracket, t squared, t whatever, but we could take L of curly bracket something times u. So the entire purpose of u is just to represent piecewise functions. We do that with this property that we put, L of f of t minus a, u of t minus a is going to be given by e to minus as f of s. And in this case, f of t minus a, u of t minus a, because u is 0 then 1, multiplying 0 by f would give us 0 still, for 0 less than or equal to t less than a. But then multiplying 1 by f just gives us that f of t minus a for any t bigger than a. So for example, what this is going to just look like as a function is, suppose I had the piecewise function tf that is 0, and then takes on value e to 3t. This is f of t equal to 0 or e to 3t. First, up until 1, it's 0. There. I'm doing the squiggly lines just so you can see it's different from the axis, not because it's a squiggly function. And then for t bigger than or equal to 1, I drew that exponential that it's taking off as. And so if I wanted to take Laplace of this function, I would need to represent it as something using that curly u. So I've got like definitely some kind of exponential thing, and I want to use u of t minus a. Whatever is inside these square brackets is that f of t minus a that I want to see. And so the tricky part here is just figuring out how to write this function. So I want to start the non-zero part of my function at 1. So I know that I'm going to be thinking of u of t minus 1. So my function f is off until 1, and then it's e to 3t afterwards. So if I just wanted to plot it, I could do this. I could say, okay, it's e to 3t times u. So it's 0, and then it's e to 3t. This is how I would represent that. But I need it to look like t minus 1. Because if you see here, I need f of t minus a times u of t minus a. So if u starts at 1, I need to see things that look like t minus 1 in my f. So I'm going to do similar to before. I'm going to say, okay, I need it to have 3t. So I guess I'm going to use e to 3t minus 1. This is 3t minus 3. So if I want to only have 3t, I would just add 3 to cancel out that extra 3 I introduced just now. So taken together, this input, 3 times t minus 1 plus 3, it does have terms that look like t minus 1, but if you kind of calculate it all out, that's going to be e to 3t minus 3 plus 3 is just e to 3t, which is the function I really want this to be on the inside. Now that it's represented in this form, I could go ahead and take Laplace. Which I guess I'll, sorry, I'm going to do an example. So please pause if you need more time here. But once I've written a function like this, I can use my Laplace property. And I want to show you how that works. So let's try to compute L of f for f equal to 20t 0, where it switches at 5, becomes 0 after 5. So this function is going to look like this. It's going to go up. I shouldn't have an arrow, sorry. It's going to go up until 5, and then it's going to be 0 after that. 0 after that. So we want to use this property, L of f of t minus a, u of t minus a is equal to e to minus as, capital F of s. But my f needs to be specified for this to work. So f is 20t at some point. I know that. But I don't know how to deal with the fact that it switches to becoming 0. Before I was used to saying it's 0 and then 1. That's represented by u. So if I want to flop that around, if I want it to be something then 0, what I'm actually going to do is I'm going to take away a u function. So at 5, I want to do something. So I'm going to use u of t minus 5. And the thing I want to do, the action I'm turning on, is that I am deleting my 20t. So I'm just going to say, okay, take away 20t after you pass 5. If you plotted this function, if I plug in t equals 0, the u of t minus 5 is 0, so I just get 20t. But if I plug in t equals 10, then u of t minus 5 is 1, so I get 20t minus 20t, or I get 0. So this is performing exactly how I'd like. The problem is that I need f to look like t minus 5, and it does not. So I say, okay, I want 20t, I will take 20 times t minus 5. That's going to be 20t minus 100. In order to balance that out, I just have to add an extra 100. And then multiply by u of t minus 5. Now this is a function that I can take a Laplace transform of. It's piecewise, but it uses u's, so everything's represented in one line. It looks like my property, f of t minus a, u of t minus a, and I can apply linearity to take care of the first part. So let's go ahead and try that. L of f is going to be L of 20t minus that 20 times t minus 5 plus 100 u of t minus 5. Separating out that last term, we're going to have 20t minus 20 times t minus 5 u of t minus 5, and then minus 100 u of t minus 5. Remember to be careful that we distribute that minus all the way over to the 100. Now I can apply linearity to break this up into several different things where I'm computing Laplaces. So I've got 20 L of t minus 20 L of t minus 5 u of t minus 5 and minus 100 L of u of t minus 5. So, for all these different functions, you know what, I haven't moved this thing down for a while. We're on the inverse example. No, we're not. We're on the regular example. Sorry, everyone. It has been a long day of recording videos. So, I'm going to go ahead and write my easiest one first. L of t, I know I've done it a lot of times by now. It's 1 factorial, or 1, over s squared. So if I do nothing else, at least I did that one right. For these two in the middle, I'm going to have to use our new property. So my f of t minus 5 is t minus 5, which means my f is just things that look like t, and my a is 5. So my big F is L of t, or just like we said for the previous term, 1 over s squared. So this is going to be minus 20 e to minus as, so e to minus 5s. I'm going to shift everything up just a little bit to make this less scrunched at the bottom. So I'll shift that one up too. At the start of the problem, I wrote like I was never going to run out of space, but I was wrong. Okay. Now you can kind of see that these are different things, hopefully. So 20 e to minus 5s times that 1 over s squared. And then for the last part, it's a little silly. So my f of t minus 5 is 1, which means my f is 1. And we're still working with that a equal to 5 inside our u of t minus 5. And our capital F is L of 1, which is just 1 over s. So for that last term, we're going to have minus 100 times e to minus 5s times our capital F, which is just 1 over s. And then at this point, we've completed the problem. We took the Laplace of a piecewise function. And that's going to be helpful whenever we want to solve an initial value problem that uses a piecewise function. So I'm going to go ahead and move on to the next video. If you need, please pause and finish up this problem on your own.